Okay, so we know that water is the amphiprotic acid, means that it can act as acid and base depends on its partner. So even if we have a pure liquid, okay, we have only H2O 100% in our sample, the water can react with itself and undergo a process which is called as the autoionization of water. So we have H2O with H2O. Okay, they will undergo ionization process, or we call it as the autoionization, and it will form hydronium ion and also hydroxide ion. Okay, so H2O react with the H2O, it produces H3O plus and also OH minus. Okay, and we can have the Kc expression for this reaction, in which Kc is equal to H3O plus concentration multiply with the OH minus concentration. Okay, divide with nothing because both of the reactant are in a liquid state. Okay, or to be specific, that Kc expression we call it as the Kw. Okay, so the Kw is the water ionization constant. And the Kw, since it is a constant, so the value of the Kw is always 1 times 10 power of negative 14. So a change in the concentration of the H3O plus will give an adverse effect to the hydroxide ion. Means that if the concentration of the H3O plus increase, the concentration of the hydroxide ion will decrease. If the concentration of hydroxide is increased, then the concentration of the hydronium will decrease, because the product or the answer of the multiplication of the concentration of both must be always 1 times 10 power of negative 14. And in any solution, both ion must present regardless of the solute. Okay, even if we have the sodium hydroxide solution, we have both. We have hydroxonium and we also have hydroxide ion. Okay, same goes if we have acid solution. For example, in the nitric acid solution, we have both hydroxonium ion and also hydroxide ion. The difference is just at the concentration of both, which one that is higher. Okay, if they are in a basic solution, hydroxide will be higher. But if we have acidic solution, the concentration of the hydroxonium will be higher. But if you have a neutral solution, their concentration will be equal. Okay, which is 1 times 10 power of negative 7. Because the product of both will be this. 1 times 10 negative 14. Okay. So if we have the concentration of the hydroxonium ion that is greater than hydroxide, we will have acidic solution. The same concentration of both, we will have a neutral solution. While if the hydroxonium is lower than the concentration of the hydroxide ion, we'll have the basic solution. Look at to the example given. We have a HCl gas that is added to the water and it produces a solution, and that solution has a concentration of the hydroxonium 3 times 10 power of negative 4, and we have to calculate the concentration of the hydroxide ion. And after we get the concentration of hydroxide, we have to decide whether the solution is neutral, acidic, or basic. Okay, so we use the Kw value, the water dissociation constant, okay, which is 1 times 10 power of negative 14. The equation is always Kw is equal to 1 times 10 negative 14 equal to the concentration of the H3O plus multiplied with the concentration of the hydroxide ion. So, since that we already have the concentration of the H3O plus here, just plug in the value and rearrange our equation, makes hydroxide's concentration as the subject. Okay, then we'll get the concentration of the hydroxide ion equal to 3.3 times 10 power of negative 11. So now we compare. Okay, this is the concentration of the hydroxide, 3.3 times 10 negative 11, with the concentration of the H3O plus, which is 3 times 10 negative 4. Obviously, that H3O plus is more concentrated than hydroxide ion. Okay, so H3O plus is more than hydroxide. The solution become acidic solution. If the question don't ask us to calculate the concentration of the hydroxide ion, it is obviously that the concentration of the H3O plus here is more than 1 times 10 power of negative 7. Okay, when it is more than 1 times 10 negative 7, then obviously that the concentration of the hydroxide will be lower than this. Okay, because if they have a balanced concentration, both will be 1 times 10 negative 7. Okay, so when we observe that 1 is greater than 1 times 10 negative 7, then obviously that it is more concentrate. Okay, we have more it present in our solution, then it is acidic. However, if the question told you that the concentration of the hydroxide ion, for example, is 4 times 10 negative 5, which is still greater than 1 times 10 negative 7, then we know that the solution is basic. This scale is the one that is commonly used in this acid base. This is because in the ecosystem, the concentration can vary from 10 molar up to 10 power of negative 15, which make it inconvenient to handle negative exponential numbers. That is why we have this numerical system, which is called as a p-scale, in order for us to use or to have only positive number. For example, if we remember the Kw value, Kw is 1 times 10 power of negative 14. Okay, so 1 times 10 negative 14 is not so convenient if we compare it with 14 only. Okay, that is why we have this p-scale. So instead of we use the concentration of the H3O plus, we can have a pH, in which pH means negative log concentration of the H plus. Okay, and then we also have a POH, which means negative log concentration of the hydroxide ion. We have a pKa for negative log Ka, pKb for negative log Kb, and pKw for negative log Kw, in which it is equal to negative log 1 times 10 power of negative 14. And if we press the calculator, we will get pKw equal to 14, or negative log 1 times 10 negative 14 is equal to 14. Okay, so this is the pH value for some familiar solution. Okay, sodium hydroxide, the pH is 14, ammonia 12, and then the blood, it is basic 7.4. Remember, above 7 they are basic, lower than 7 they are acidic. Okay, we have HCl, 1 molar, the pH is 0, stomach acid, it is between 1 to 3, and pH is equal to negative log concentration of the hydronium ion. Okay, so the relationship between the pH and also the concentration of the hydronium ion is lower the pH value, the higher the concentration. And the higher the concentration of the H3O plus means that the acid is a stronger acid. If we have a higher concentration of the hydroxide ion, the POH value will be lower. So the lower the pOH value, the stronger the base. So that's the relationship that we have to remember. The H3O plus concentration inversely proportional to its pH, directly proportional to the strength of the acid. Concentration of the hydroxide ion is inversely proportional to its pOH, and it is directly proportional to the strength of the base. So the concentration of hydronium ion and hydroxide ion also can be related by using Kw. Okay, because the Kw, as what we have learned before, Kw is equal to the concentration of the hydronium ion multiplied with the concentration of the hydroxide ion. Thus, since that concentration can be related, pH and pOH also can be related. Okay, so pKw, which is equal to 14, is equal to pH plus pOH. So we look at to the example of the solution. Okay, basic solution. If let's say we have a solution with a pH of 12. Okay, solution with a pH of 12, because of the concentration of the hydroxonium ion is 1 times 10 power of negative 12. So when we press the calculator, negative log of this figure will be 12. Okay, and for this solution, the concentration of the hydroxide ion in it is 1 times 10 power of negative 2. And we press the calculator, negative log of this will be equal to 2. So that the pH of this solution is 12, pOH is 2. Okay, so we know that when the concentration of the hydroxide is greater than the concentration of the hydroxonium ion, we know that the solution is basic. For the neutral one, the concentration of the hydroxonium ion is 1 times 10 power of negative 7. Press the calculator, negative log of this will get the pH value of 7. And the concentration of the hydroxide ion is the same as this, 1 times 10 negative 7, and the pOH is 7. So neutral solution will have a balanced amount of the concentration for both ion, and the pH pOH value will be equal, which is 7. As for the acidic solution, let's look at to this solution that have a concentration of the hydroxonium ion 1 times 10 power of negative 4. Its pH will be 4. The concentration of the hydroxide 1 times 10 power of negative 10. pOH is 10. Okay, because we know that the pKw is equal to pH plus pOH. So pKw is 14 just now, is equal to 4 plus 10. Okay, now relationship between Ka and pKa. Here, all acids that has Ka value or acid dissociation constant, they are weak acid. Let's look at to one example here, hydrogen sulfate ion. The Ka value is 1 times 10 negative 2. pKa is 1.99. So it is more convenient to handle this type of number as compared to this one, 1 times 10 power of negative 2. Phenol, Ka is 1 times 10 negative 10. The Ka is 10. So the relationship between these two, Ka and pKa, is the greater the Ka value, the smaller the pKa value. They are inversely proportional. Same goes with the Kb and pKb. So these are some methods in lab that we can use to determine the pH of the solution. We can use pH paper. And then if we want it to be more accurate, then we can use a pH meter so that we can get up to 2 of or 3 decimal place pH value. Okay, so let's look at to December problem 18.3. Okay, so this question asks us to calculate the concentration of the hydroxonium ion, the pH, concentration of the hydroxide, and also the pOH for 3 different concentrations of the nitric acid. Okay, so the method is, firstly we have to calculate the H3O plus concentration, since that this is the strong acid. So the concentration of the acid is equal to the concentration of the H3O plus, which is 2 molar. And then press the calculator, we'll get the negative log 2 equal to negative 0.3. That is the pH value. And then the pOH, okay, we calculate hydroxide's concentration first by using this equation, Kw over concentration of the hydroxonium ion, and it is equal to 1 times 10 negative 14 over 2, which is, the answer is 5 times 10 negative 15 molar. And then we press the calculator, negative log of this, in order for us to get pOH, then the answer will be 14.3. So we know that pKw is equal to pOH plus pH. So 14.3 plus negative 0.3, it is equal to 14. So I want you to answer on your own. Okay, how to calculate the H3O plus, concentration, pH, pOH, and also the hydroxide's concentration for another 2 different concentrations of the nitric acid.